welcome back. So in this video module, we'll talk about balancing chemical reactions and then using dimensional analysis to convert between grams and moles of reactants and products in a balanced chemical reaction. So let's go ahead and just get started. Okay, so a few tips and tricks you should keep in mind when balancing a chemical reaction. So tip number one is if a reaction contains only carbon, hydrogen, and oxygen, meaning likely it's a combustion reaction, you want to balance the elements in that order. So you should balance the carbons first, the hydrogens next, and then the oxygens last. So let's take a look at a quick example. So here we have a combustion reaction, right? A hydrocarbon, C5H12, burning in the presence of oxygen always releases the two products, CO2 and water. Okay, that's always what a combustion reaction looks like. So let's go ahead and try to balance this guy. Okay, so as I mentioned first, let's start with carbons. Okay, so I have 5 on the left and I only have 1 on the right, so I'm going to put a 5 here. Okay, so now that I balanced the carbons, let's do the hydrogens, right? So I have 12 hydrogens on the left, I only have 2 on the right, so I'm going to put a 6 right here. Okay, to balance the hydrogens. And finally, I do oxygens last. And the reason that I do oxygens last is because oxygen appears twice on one side. And whenever an element appears twice on one side, you want to balance it last, right? Because as you add numbers, you kind of mess things up. So save that for last. So let's count. See, I have 5 times 2, right? Because I have 2 oxygens. So 10 oxygens from CO2, 6 oxygens from H2O. So that makes 16 oxygens on the right. So in order to make that work, I need to have 8 right here, right? And if something's just a 1, you don't really need to write it. Okay, so it's just a number 1 right here. So if you just count, I have 5 carbons on the left, 5 on the right, right? I have 16 oxygens on the left, 16 on the right, and then 12 hydrogens on the left and 12 on the right. So let's do a second example. This time it's a little bit different because instead of having a hydrocarbon, you have a carbohydrate, which has carbon, hydrogen, and oxygen. Burning in the presence of oxygen creates CO2 and H2O. So let's balance this guy too. Okay. So as before, let's start with carbon. So I have 2 carbons on the left, only 1 on the right. So I'm going to put a 2 in front of that guy. Let's see my hydrogens next. 6 on the left. I only have 2 on the right, so I'll put a 3 in front of there. And finally, my oxygens. Okay, so let's keep track of this. So I have 4 oxygens from the CO2, and I have 3 from the H2O. So in total, I have 7 O's on the right. On the left, right now I only have 5. So here, I have 3 O's. Okay, so what I need left is 4. So this guy needs to have 4 O's, 4 oxygens. So I put a 2 there, right? So this is going to be 1, 2, 2, 3. Okay, if you check, every time you balance an equation, make sure you check to make sure that you have the same number of elements on the left as you do on the right. Okay, so balancing equations, very important, right? It might seem pretty trivial right now, but you have to know how to balance equations to do the problems for this course. Okay, tip number 2 is start by balancing atoms that appear only once on each side, right? As I mentioned before. Okay, so let's do some examples. All right, so okay, let's start with this guy. Okay, so let's start with an element that appears only once on each side. So that's arsenic. Okay, there's 4 arsenics on the left, and there's 2 on the right. So let's go ahead and put a 2 here. Okay, and so which element should we balance next, right? Not oxygen, because oxygen appears twice on the right. So let's do sulfur instead. I have 6 on the left. I only have 1 on the right. So I'm going to put a 6 over here to balance the sulfurs out. And then finally, I do oxygens. All right, so from here I have 12 oxygens. Here I have another 12. So in total on the right, I have 24 oxygens. And so my left needs to also have 24. So I'll put a 12 here. And here I put a 1. Okay, so 1, 12, 2, 6. Let's try the next one. Okay, so this one, let's start again with an element that only appears once on each side. So an example of that's going to be lithium, right? I have 3 lithiums on the left, 1 on the right. I want it to have 3, so I put a 3 right here. Okay. Let's look at another element. Well, let's do nitrogen, right? Nitrogen's already balanced. I have 1 on the left, 1 on the right. I don't have to do anything there. Finally, let's do hydrogens, okay? Well, actually, let's save hydrogens for last because it appears twice on the right, let's do oxygens next, okay? I have 3 oxygens on the right. I only have 1 on the left, so I need to put a 3 here, all right? Now that I put a 3 in front of this hydrogen, I know that I have 6 on the left, and I need to have 6 on the right, and lo and behold, we do, right? Because this guy is a 1, okay? So here all my elements are balanced. Okay, and let's do finally the last one. Oh, and by the way, this first number is 1. Okay, and then the last one, let's start with, let's see, oxygen, right? So for my oxygens, I have 3 on the left and only 1 on the right. So I'm going to have to put a 3 there to balance the oxygens, right? I'm going to save xenon for last, right? Because it appears twice on the left. For my fluorines, now I have 12 fluorines on the right and I have 6 on the left. I want to make sure that it has a total of 12. So I put a 2 in front of there. And then now that I do that, if you notice, my xenons are actually already balanced because I have 3 on the right and then 3 on the left. Okay, so that's some more practice problems for balancing reactions. Make sure you're very comfortable with this. Okay, so let's use dimensional analysis to solve some problems. Dimensional analysis is just a fancy term for converting between units of one thing to another. So specifically, you want to convert between grams and moles, and vice versa, moles to grams as well. And you want to do this for both the reactants and products, okay? And if there's more than one reactant, you should be able to also do that for um, interreactants, so between reactants, as well as between products, all right? So let's try an example. Okay, so it says, consider the following reaction, and it gives us this reaction. Calculate the mass of Li3N, so needed to produce 5.7 grams of LiH, okay? And then here I'm already, technically, usually this wouldn't be given. These are the molar masses of these compounds. Usually you'd have to use the periodic table to calculate that, but here, for the sake of convenience, I'm giving it to you, okay? So let's go ahead and try to do this, and we're going to use dimensional analysis. So the first thing that I always do is figure out, so I underline, this is what we're looking for, right? We're trying to calculate mass of Li3N, and the only information that we're given is this, okay? So you always start with the information that you're given when you're doing a dimensional analysis, okay? So we start with 5.7 grams of LiH. That's all we know. And ultimately, I want to convert this to grams of Li3N, okay? But before you convert from grams of one substance to another, you have to go convert the LiH to moles, okay? So you can't convert grams of one molecule to the grams of another molecule. You have to go from grams to moles, right? And then from moles of LiH, you have to convert that to moles of Li3N, and then from moles, you go to grams. So grams to moles to moles to grams. So that's exactly what we're going to do, okay? And we're going to use dimensional analysis. So I'm going to multiply this guy by a factor, okay? Basically, I'm going to use, and in order to figure out that factor, I use the molar mass. So for LiH, in order to figure out how many moles that is, I use 7.95 grams per mole, which is up here. So I put that at the bottom because I want the units to cancel. I want my G's to cancel, my grams to cancel. So this is grams of LiH. And then on the top, I'm going to put 1 mole of LiH. All right? And then in doing so, my grams of LiH cancel. Okay? So now that I have moles of LiH, I need to convert moles of LiH to moles of Li3N. Okay? And in order to do that, I have to look at the equation, right? The reaction. Okay? And there's one important thing you always have to do when you're given a reaction, and that's to make sure that it's balanced. Okay? And if it's not balanced, you have to balance it. So let's go ahead and look at this. Okay, let's balance it. So at first it might look a bit tricky to balance, but let's give it a shot. Okay, so I have 3 lithiums on the left. Here I have 2 on the right. So one of these lithiums is going to have 2. All right. I don't want to mess with this nitrogen because I already have 1 on the left. So I don't want to mess with this one. Right. I want to keep this a 1. So I'm going to put this guy, I'm going to make this guy a 2 so that I have 3 lithiums on the right and then 3 on the left. Okay, and so now I can figure out what I need to do, okay, because I need to balance, So my lithiums are balanced. My nitrogens right now are also balanced. The only thing that's not balanced is hydrogen. So I have 4 on the right, and so I need to have 4 on the left, so I put a 2. Okay. Now that I have my balanced reaction, I can use these coefficients, right? Here's a 1, here's another one. I can use these coefficients to convert from moles of one substance to moles of another. Okay, so here I need to convert from moles. So here I'm going to put moles of LiH. Okay, so basically what I'm going to do is use these coefficients to figure out what factor I need to multiply by. Okay, so for every 1 mole of Li3N, I form 2 moles of LiH. So on the bottom, I have to write moles of LiH. And actually, I miswrote here. This should be a 2. Okay, 2 moles of LiH. Because for every 1 mole of Li3N, you form 2 moles of LiH. Okay, and then after this, you can go ahead and multiply, okay, because I have grams to moles of LiH to moles of Li3N, and I'm very close. So finally, I need to convert moles to grams. So I have 1 mole of Li3N on the bottom, right, because I want that to cancel. And then I put the molar mass of Li3N on the top, which I gave you at the very beginning, which is 34.83 grams. And that's of Li3N. And then you put this in your calculator and you solve. Let's go ahead and do 3 significant figures, 3 sig figs, because they give you 3 sig figs, and you should get 49.9 grams. And that's your mass of Li3N you produce when you start with 5.7 grams of LiH.